Um, but yeah, that's a recent fly-through that Space Telescope made for us with all the actual JADES images for the objects as you fly out to JADES GSC-14, which I really like. So anyway, I'm Kevin Hainline. I'm from the University of Arizona. I'm a member of the JADES team. Here's our fun smiley picture of the JADES team. This is the best I could do for getting one where Brant is smiling. If you've not gone to our website and looked at the incredible FITS maps that have been put together so you can go and look at all of our publicly available data, it's a huge amount of work that the JADES team and specifically Brant and Ryan Housen have done to put this together. But also we have a lot of our data public and we encourage you all to use it. I'm going to talk today about what JADES has shown for the high redshift universe above redshift 10. And this is a real triumph of a figure. Before JWST, I did not expect this would be what we'd see after 2 years in terms of the spectroscopically confirmed objects. And then I put a couple of some of my photometrically selected objects, but there's so many thousands of photometrically selected candidates across many different teams. It's a real triumph from the field, and we should all feel very proud about all of the work that's gone into finding these galaxies. Caitlin did a great job of talking about some of the really bright ones, which really stand out up here, right? Like GLASSY 12, GSC 14, GNSC 11. I'm going to talk a little bit about some of the fainter ones up here as well, and I'm going to talk about some of the stuff we've learned photometrically from JADES objects from the spectra. At the end, I might talk about some of the lessons learned, just a couple little things that I wanted to throw in here for this group. But my goal with this is, it might seem a little scattershot, but to kind of essentially say to everyone, like, here are some of the things we should be thinking about, like some big open questions that especially if you're a theorist in the room, that we want to really talk about. If you're unaware, this is JADES. It's about 224 square arc minutes. This is from our current reductions. There's some extra stuff included on here that's not in the yellow, some from Panoramic. NG Deep is sitting up here. But you can see all of these, and you can actually see that we have quite a few filters here. You just march through all the filters to see that, like, we really have a fantastic data set. You can see Fresco, which is what causes these big boxes in a couple of the medium bands in F44. But it's a really incredible legacy data set that I think, in terms of just the filters, is fantastic. The filters have allowed us, the number of filters have allowed us to do a really good job of photometric selection of high redshift candidates, in that instead of having just 1 or 2 detections like with HST, where we'd have like one F160 detection and be like, this is a really high redshift galaxy, some of these high redshift galaxies have many, many bands of detections, which is really great. Like, here's an object from Brant Robertson's paper, which is in the origins field, which just has, so many medium and wide band detections. It really gives us confidence in the photometric redshifts of these objects and in their validity. This one's just in part of the region that doesn't have F335, part of our data. Really, really great. From the photometric selection, we can do things like Michael topping. I should say that many of them are compact, but we're actually pretty stunned that some of these objects, here's at redshift 10.4, 11.3, have multiple components. And this is, not as rare as I would have thought. That there's quite a few of these objects that, like this little croissant or this little dog bone here, that like have these multiple components at a pretty early era, which is very exciting. The photometric selection allowed for us to look at the things like the UV slopes. So Michael Topping wrote a paper with the JADES UV slopes, where you can see here that the UV slope is on the y-axis and MUV. At a given MUV, it seems as if there's an evolution, and you can see the version up here where MUV is at negative 19. But there's an evolution towards bluer UV slopes as you go to higher redshift. There's many groups that, like, this is not a, this is still in debate in terms of whether or not we're really seeing this, but we're getting pretty blue UV slopes at the highest redshifts. And we're actually approaching a point where the UV slopes are so blue that we have to invoke models that have a non-zero escape fraction. So here's something where he's fit one of these objects with a kind of standard, stellar population synthesis model, but then, the fit gets significantly better if you allow the escape fraction to go, much higher. And you can see here, if the escape fraction is 0, you get much larger chi-squares than if you let the escape fraction go above 0. And so this is something we'll talk about in a little bit as well, but it's seen in our photometric samples. So let's talk about some of the spectra. This is a spectra for for JADES GSC 11, which is 11.122, where we took a 75-hour exposure and finally were able to see these, very, very faint optical emission lines out here, O2 and neon 3. putting it at 11.122. And it's seen somewhat, at low significance in the grading spectrum, not just the prism spectrum here, which is really exciting. But this is something where for, GNZ11, for some of these really, glass Z12, you get these, pretty strong lines. But as you go down to lower MUVs, or to fainter MUVs, you really have to get very, very deep exposure such that you can actually see some of these very faint emission lines in these spectra. GSZ12 here from Francesco Diogenios has a pretty solid detection of carbon-3. There is some evidence that there might be some other lines, but they don't line up with the redshift implied by carbon-3 here. But we're seeing this. This carbon-3 detection implies maybe a supersolar carbon-to-oxygen ratio for this object. But really, this is a heroic effort of spectroscopy to get down to these very faint limits to see these emission lines. This is a very exciting object that is in a paper by Joris Witzak. It has not come out yet, but this is an object at redshift 13, and I don't know if you saw this, but that's Lyman alpha. Right here, you can see it's significant. We have two different visits that show it in both visits, but this is a detection of a Lyman alpha emitter at a redshift 13 galaxy. It is not, I heard a very low whistle from someone right now. It is not oxygen 2. The Balmer break would not work with this being at oxygen 2. This paper is coming out hopefully next couple weeks to a month or so. But this is a very exciting thing, especially because this slope is also about negative 2.7. So it's something where this is not a nebular continuum. It also potentially implies that you have a non-zero escape fraction. But it can't be, it has to be something where you can balance escape fraction and the fact that you see Lyman alpha in emission here. But this is a very, very exciting object, JADES GSZ 13L1LA. But then once you get to higher redshifts, it becomes very hard for us to find emission lines. So this is GSZ 13.0, where we take a 56-hour spectrum and see no evidence for strong lines. Some of these look like them, but when you look at the individual visits, we don't see anything. And what's interesting about this is that the slope on this, combined with the fact that there's no emission lines, is actually very difficult for us to model. So when we, it's unlike some early papers that claimed that it was unresolved. The galaxy is actually just barely resolved. It's not just a dark star or something. It's a real galaxy. It's hard for us to model this. This is our model where we allows the F escape to vary. You actually end up getting the slope correct, getting no emission lines, and allowing for, but you get a pretty high escape fraction. If you then essentially say, well, okay, if you make the escape fraction fixed, then it becomes really hard. You get very low metallicities, you get very low ionization parameters, and you can't even reach the slopes that you need. If you allow a burst, you can, with some delayed star formation history, you can do it, but it really requires that all of your stars that had a burst like exactly 10 million years ago, and then no star formation since then, which is kind of arbitrary. So this is pointing to the fact that we're actually seeing these high escape fractions in these high redshift galaxies. Here's GSZ 14.0. I'm skipping over GSZ 14.1. I'm sorry, it's very similar. It has a very similar spectrum to the one I just showed you there. But this is 14.0. Caitlin talked a lot about it's very UV bright. It's also excitingly very extended. So this is something that's really, really weird about this, is that UV radius is about 260 parsecs, which is kind of enormous compared with how big this one is. Just, this object's 20, 30 parsecs, and then something that's like 10 times bigger. This is a very, very exciting discovery. And to Caitlin's point, this is a plot that proves that the universe has a cruel sense of humor. This is the neighbor that Caitlin was talking about right here. You put a slit on the neighbor, we put a slit on the actual object. Look where the Balmer break is. Look where the Lyman break is. This is really rude. This is something where the actual reason why, one of the major reasons why we did in fact go after this was not just from the photometric detection, but also grad student Jake Helton, who's going to be talking later this week, came to us all and was like, did you know this thing is brighter in MIRI than it is in NIRCam? And so here's a NIRCam image, and then the F27, and then the MIRI F770, and you can see that it's really, really booming at 7 microns, and that's because we think there's probably oxygen 3 plus H beta that's boosting that. And so this is something that really led us, along with Brant's work with the JADES Origins field, looking at it again with more filters, to really go, we got to get a spectrum of this. And we were very excited when it turned out to be at about a redshift of 14.32. This is something that has been seen in the literature in terms of MIRI. MIRI has detections of, here's an object at Redshift. This is glass C12, which has they have a full spectrum showing MIRI with oxygen 3 NH alpha. And just like last week, there was one of this MAX 0647, which it was a lens object that also has a detection. So this is actually pointing to the fact that MIRI, and I'm expecting in cycle 4, MIRI is going to be a pretty exciting Redshift machine for a lot of these things, and that we're really able to see some of these rest frame optical lines for these really massive galaxies. What's exciting about GSC 14.1 and 14.0 is if you just, take some naive assumptions about the way that halos evolve over time, is that these are actually going to evolve into really, really bright objects, and we just, we in this figure don't have them. Caitlin showed a figure that showed, oh, this is exactly where these are born, and that, the objects from Cosmos Web that they find up here are where a lot of these things are evolving into. The most recent Lily Whitler, who is a graduate student at University of Arizona, she's been working on a full JADES luminosity function, and here's the most recent F115 and F150 dropouts compared with Brandt's JADES origins field luminosity function, showing that we actually have, pretty good agreement with other things in the literature, and there's quite a few very luminous objects, to what Caitlin was saying an hour ago. So some lessons learned. First lesson learned is something that I think we need to talk about this week, hopefully, which is that the turnover of the Lyman alpha break is far smoother than what is, seen or used in many fitting models, implying potentially something's going on. Casper Heinz thinks that it is strong, damp Lyman alpha absorption that seems to help explain some of this thing, but it also means that your photometric redshifts are biased high. And that's a thing that's been seen by many different groups, and it's something we have to take into account in our new thing. And then something else that I think is really, really important, and it was brought up earlier, is that many of our, we have a number of F200 dropouts in our survey that, they seem pretty red in their SED fits, and they just turn out to be supernova. So what you see here is the 2022 image from JADES and the 2023 image. Hello, goodbye, hello, goodbye. And so you see in F115, 200, and 277, it disappears. Same thing here, right? Another object that looks like it should be a Redshift 16 object, very, very bright, and then it is in fact a supernova. And there's a third one that we found that I'm not showing here that because we don't have the short wavelength data for it, but it was also, had a slightly bluer slope for this. But this is something where we have to be very wary that the 4,000 angstrom break in a supernova spectrum can kind of redshift and really, really trick us if we don't have multi-epoch observations. And so I think that that's it for my time. Here's my conclusion slides. There's so many exciting things about the high redshift universe. I know that was a huge amount of stuff, and I'm excited this week to talk to people about, what we can do with better fitting and better understanding this. But yeah, thank you very much.
Thank you very much. Okay. Questions? Let's start with Harley. In the back, Benna?
Oh.
Sorry.
Oh.
Hi, Kevin. Thanks for the very nice talk.
Thank you.
Can you talk a little bit more about the measurements of the escape fraction? In particular, 80% is really high. Mm-hmm. And when you have a featureless spectrum, what feature is the SED fitting picking up on that actually lets you define an escape fraction that's 80%?
It's mostly the fact that you have no lines combined, well, not this one, but no lines combined with the fact that the slope is very blue. The slope is negative 2.8. If there were any nebular continuum, it would redden the whole thing. And so it's something where trying to model that has been very, very tough for these codes.
But for the Redshift 14 objects, mm-hmm. where you also predict a high escape fraction, the UV slope is minus 2.2, and it's also very high. So it's just not exactly clear to me. How do you know that the cloudy models and the SED fitting codes and the underlying shapes of the SEDs are robust at all? Can you try this on green peas and see if you come up with the right answer?
Yeah, I think that this is the Redshift 14 object is just weird overall. GSC 14 is very strange. I don't understand, some of the modeling that how that worked exactly. But I agree. This is a thing we need to explore more, right? I don't, it's a very high escape fraction, and it's, Okay,
Andrea.
Thank you very much, Kevin. Concerning the GS 13.1, the Lyman alpha emitter.
Yeah.
So this is very amazing that you have Lyman alpha escape from redshift 13 in the neutral IgM. So I'm wondering, my take would be to say that it's likely this galaxy has an outflow that is helping the escape of the Lyman alpha photon, but there could be other possible explanation. Do you see any signs, or do you have any indication from the data, for example, the shift of the peak of the line? Or
well, the modeling of this is, again, this is very preliminary. The paper is still working. Like this has to be like, Joris has done a pretty good job of modeling this, and it would, the based on the models that he's done, it looks like it might be a 600 angstrom equivalent with, as like observed here is like a 40, but like we're probably just some observations, and we'll put the redshift instead of 13.04, maybe 13.01 or whatever. But like that's hard to say because we don't have like a systemic redshift for it. So we just have what we have here. There's just one line.
Okay, Mark.
Since you've got that slide up and you were just talking about damping wings, I don't know how much, given, as you just said, this paper is, still being worked on, so I don't know how much you want to talk more about it. But I mean, it strikes me that the Lyman alpha line is where the continuum has already dropped to 0 on this, which, I was just wondering if you wanted to say anything about putting the Lyman alpha and the damping wing part together, and what this, what
Yeah, you may have to wait
interpretation would say about that.
Yeah, you may have to wait for Joris's full paper here. This was something where I got permission to show this from Joris, but he's still working on the paper. But there's a full treatment modeling this with the potential damping wing as well.
Okay.
Yeah. Sorry.
Other questions? Let's take one from over here.
Another question about the Lyman alpha emitter.
Yeah.
Any indication that this could have an AGN?
No, actually, there's not. I mean, like from what we see here, there's not any of there's no UV lines. There's nothing like, this is essentially mostly what we have here from the photometry here is, if, you can see it plotted, it's effectively around the same, but that there's no evidence from what I see and what we see of any other, UV lines that might indicate this. No helium or anything.
Joe, do you still want to ask a question? No? Other questions? Sorry if right here, please.
Sorry. I have a really ignorant question. You talked about these transient events and looking for multiple epochs of observation. What would that mean? Like, are you talking about longer spectroscopy, like 56-hour exposures, or like?
We got to take more. You got to
now?
go back to the same regions and take another image, right? Like this is something where, because JADES was taken over a couple of years, we're able to go back and look. And so there, Krista DeCourcy, who is the grad student who put this all together, like she did a valiant effort of looking at, the different images to try and find supernovae. But as part of that, a number of the objects from my own survey, were like, oh, no, this object just disappeared in this. Or we got very excited and we had another epoch of observations in another field. We're like, oh, this is great. Look, this is a new F200 dropout or whatever. And it turned out, no, you didn't see it, in the previous ones, and you did. And it's hard. You got to watch out because sometimes you want to stack all of your stuff when you get multiple epochs. But really looking between the two, like this is something that I worry about for, any of the surveys where we just have this one big, field, is that like how many of those, if they go back spectroscopically, you're just not going to see it because it was a supernova, right? I mean, it should be good for people writing proposals. Look, you just can point to this and be like, we got to get it, because otherwise, how are we going to know? And it's a real rich thing. There's lots of these, in Krista's thing, we have redshift, high redshift, redshift 4, redshift 5, like supernova, which is very, very exciting, but it's also a warning.
Any last questions? Yep, go ahead, please.
So in many of the spectra you showed, the rest frame UV continuum seems to have some features that don't look like just pure Gaussian random noise. So are they artifacts, or some of them could it be physical?
It's probably not physical. It's hard to say. It's like some of these, especially over here, right? Like these are faint, and we're really like, but it's. I think that it's pretty consistent with just being noise, right? Like especially because for some of these, like for this one in JZ11, we have two entire separate observations. We observed it a couple years ago. for the initial confirmation, and then we reobserved it to get deeper to hopefully get at some lines. And when we look at the two, there's not something that like, oh, it's just you see it in both of them. Like it's, this is how we can know that we can feel confident in the lines we saw for GSC 11, is that we actually can see them kind of faint in both, and then together they make a confident detection.
Thank you.
All right, let's thank Kevin again.
Thank you.